fossilized leaf and it's down to only 30% of the normal carbon-14, you want to know how old the leaf is. So the first thing you have to do is find K using this information. The half-life of carbon-14 is 5,600 years. Has anyone ever heard of a half-life before? We haven't talked about it this year, I don't think. So a half-life is, let's say I start with 100 grams of something. How long will it take till I only have 50 grams left? So in this case, it's going to take 5,600 years. And then how long will it take to have 25 grams left? It'll take another 5,600 years. So when you have radioactive material like at Chernobyl, meltdown of a nuclear power plant that leaks out into the environment, whatever the half-life is to get rid of that material, it's still going to be around for a long time. If it has a 50-year half-life and you dump a massive amount into the environment, it's going to take 50 years and you'll still have half of it left. So it's really bad to get into the environment. I don't know how many years it is, but this one, think about how long. This is why they can use carbon, because it's that many years to decrease by a half. So to find the value of K, what you're going to do is you're going to pretend, it doesn't say how many grams I start with, so I'm just going to pretend I start with 100 grams. A half-life means now I only have 50 grams left. So I'm saying I'm making up this initial amount, and then the current amount is half. So if you start with 20, you could use 20 and 10. Or you could say that you start with 10 and you end with 5. It's just half as much. E to the K times 5,600. We don't know the rate, but we do know it took 5,600 years. We want to solve for K in this equation, which is exactly like we were doing yesterday with our log method. So your first step is to divide by 100 on each side. That just turned into 0.5, right, as a ratio. So it doesn't matter what you start with. If you started with 20 and you ended with 10, or you started with 1,000 and you ended with 500, your first step, you're going to end up with a 0.5 on the left-hand side if it's a half-life problem. All right, how do I solve for K? This exponential piece is by itself, right? So I can change it into a log equation. The log base E, which is the natural log, of 0.5 equals K times 5,600. So I can type the natural log a button of 0.5 on my calculator and divide by 5,600 to find K. So don't change the base, just use the natural log button, natural log of a half, and divide by 5,600. It should be a really, really small number. So do you see how there's that E -4? That means you're sliding the decimal place 4 places to the left. So I'm going to write it down as a decimal, -0.000, what, 1, 2? So see how I slid it 1, 2, 3, 4 spaces to the left? So that would give me 3 zeros and then 1, 2. I'm going to use this value on my calculator for the calculations. This is just so I have something to write down on my paper. All right, we didn't answer their question yet. We found K. So for this carbon, I can take any leaf and now calculate how old it is. So I found a leaf. It has 30% of its original value. So you can see that they wrote, now we use this formula. So instead of starting with 100 and ending with 50, they're pretending they started with 100 and ended with 30%. So their ratio on this side is 0.3 now, equals E to the KT. So they just skipped that step. But if you want to write the step down, they pretended that they ended with 30 grams and they started with 100, right? And we know that K is -0.00012, but we don't know T. So they started by dividing by 100 on both sides. So 0.3 equals E to the KT. So we're going to solve this the same way we just solved the problem on the left. We're going to convert it into log form so we can type it into our calculator. So you're going to get really good at putting it into log form. So I'm going to do the log base E of 0.3 equals that K value. I got to solve that equation, right? Take the natural log of 0.3 and divide by the K value. I would use the complete K value that's on your screen still. Let's see how different we come out if we do the rounded one. What did I say? Negative 0.00012. It comes out by a difference of like 300 years. So, so when I took the natural log of 0.3 and divided by all the decimals, I got that the leaf was 9,700 years old. When I used the rounded value, I got that the leaf was over 10,000 years old. So I would try to use the full value of all the decimals to be the most accurate. Now, if you're dating like a leaf that's, or whatever, fossil that's centuries old, you know, at least we're kind of in the right ballpark. But if you were trying to date something of like forensic evidence of like down to the hour, you know, of when, you know, something started breaking down in the body, you want to be pretty precise, right? You don't want to be off by 3 hours of when something happened. So you want to be as precise as you can when you calculate something. So that's the process. 9727 was the age, right? 9727. That's the process. We're going to practice it a few more times today. So I'm going to skip Newton's law of cooling for a minute, just because that's another application of this work, and skip over to the guided practice, because we're going to do kind of the guided practice together. We're not ready for it to just be practice yet. I have some practice that you can do at the end. So, all right, here's another half-life problem, right? So we got strontium 90. It's a radioactive material and it decays according to this equation. Oh, they're giving you the K value. Isn't that nice? So what is the half-life? They want to know how long is the half-life. We got to solve for T. We have a couple other variables here that we need to put in numbers for. So if it's a half-life problem, you get to make up the starting amount and the ending amount yourself. I always use 150, but you could use 20 and half of it, or 12 and 6, anything that's a half, right? So if I start with 100 grams, I end with 50 grams. Because your first step, no matter what numbers you pick, is you're going to get 0.5 on the left-hand side of your equation. 0.5 equals e to the kt. So now that I got you to that step, can you finish solving for t by converting it into a log equation? So the e is the base of the log. The 0.5 goes in the log. See if you can finish solving that one for t. 4 years, 28.4 hours, that would be kind of short, but you could have something that decays very rapidly and is just gone. All right, so let's see, number 2. Actually, let's skip number 2 for a second. Why don't you see if you can set up number 3? Because number 3, again, deals with a half-life. So they're giving you the t value, right? So before you even get to this next part of the sentence, you need to solve for k. So the first sentence is all you need to solve for k. So take the half-life for t, solve for k, then once you know what k is, then you can do the second half of this problem. If 10 grams are present now, how much will be present in 50 years? So step 1, see if you can set up with this first sentence only, solving for k. Right? Model it right after how we did it on example 3. Right? We solved for k in example 3, got our k value. Once we knew k, we tried to do the leaf. I'll give you a minute and just see if you can set it up for k. Struggling through it here. Exponent. That's why you switch form. So it's the same process every time when you're solving for a half-life. And when you get it on your screen, it looks like this. Negative 4.1 but it says E negative 4 over here. So that means there's 4 decimal places to the left. Don't just write down a K value of negative 4.1. That's a really big K value. That would be a very quick decay. So a K value of this little small guy, that's going to take 1,690 years to get broken down. So now you're going to do part 2 of this problem. If you have 10 grams now, so that's your A sub 0, how much will there be in 50 years? That's your T. So now you'll have everything for the right side of your equation. So see if you can solve for how much will be present in 50 years. Bacteria question. So it says a culture of bacteria obeys the law of uninhibited growth. So that immediately tells you you're using that same formula, A sub 0 e to the kt. So it says if 500 bacteria are present initially and there are 800 after 1 hour, how many will be present after 5 hours? And how long will it take the population to reach 1 million? So there's a lot to unpack in this problem. So you're the scientist, right? And you are studying your bacteria culture. You start with 500, and after 1 hour, there's 800. So let's stop right there. We need to find K for this situation before we can figure out anything else. So A equals A sub 0 e to the kt. What do I know? I know that I'm starting with 500 bacteria. That goes in for my initial value. Remember, this 0, that's not doing anything. That's just telling you that this is initial value. We grow to 800 after 1 hour. So E is just E. I don't know K, and 1 hour has passed. Should K be a positive or a negative number? Positive, because we've got bacteria growing, right? So K is going to be a positive number this time. So go ahead and solve for K. Divide by 500, switch into logs, and solve for K. Same process every time. Move it down here. All right, so you were solving for K. Your first step is divide by 500. You get 1.6. Switch it into log form. The base is E, 1.6, K times 1 is just K. So you're really just taking the natural log of 1.6 on your calculator. So 0.47 is your positive K value. So see if you can use that to now solve the other 2 questions that they're asking. So they're asking you now, how much will be present after 5 hours? For this one, why don't you start back at the 500 bacteria? So start at 500, go 5 hours, see what you have. Don't start from the 1 hour, 800, right? Start from initially, if there were 500, how many will there be present after 5 hours? That's one calculation, right? Solving for the population. And then part 2 is how long, so you're solving for T, would it take the population to reach 1 million? So for that first part of the problem, you want to know how many will be present. If you're starting at 500, we know that K is 0.47 and it's been 5 hours. So this should be the easier calculation because you have everything on the right side figured out. And then see if you can figure out the second part of that problem. So I got negative 0.235. So I took my 39 divided by 79 was 0.4937. So you're basically taking the natural log of 0.4937 and dividing by your 3 minutes to get K. So now that we know K, now we can do some work with K. So now it says, how long should he wait before drinking his tea, right? And we can think of it as currently the tea is 60 degrees. He wants to wait how many more minutes until the tea gets to 40 degrees. And this is a tough formula to set up because of all the things, but I think if you have this model for you up here, right? 60 was what it had cooled to. We now want it to cool to 40 over here, right? 100 was the initial temperature. Now our initial temperature it's starting at is 60. So we went from 100 down to 60. Now we're going from 60 down to 40. And instead of knowing my time, now I'm going to know the K value. So my new formula would be 40 equals still 21, 60. So I'm cooling to 40 starting at 60. E to that negative 0.235 T. So now you're going to follow the exact same steps that we did for the first equation to solve for T instead of K. Should he wait 1 more minute? Should he wait 5 more minutes? When will it be ready? Restaurants need to know this, right? When they put the food under a heating lamp, they want to make sure that it's going to cool and be the right temperature when they take it out, or you ladle boiling soup. You don't want to burn your customers' mouths. You might need it to sit for a minute before it gets served. Or taking a flaming hot pizza out of the oven. You don't want to bite into cheese that's 400 degrees, right? You want to wait till it's palatable. So it's important even for food service that you know the rate of cooling under your heat lamp or in your kitchen. So you're going to solve for T, and then you can try, there's one more Newton's law problem for us to end our day on the next page if you think you've got it. I can check your answer for you and we can see if you got it. All right, now we're going to try number 4. So we're cooling to 300. So now we're solving for K in this problem. So K comes out to negative 0.1004, and then you need to resolve to get to 135. So when you solve for T, T comes out to 12.6 minutes. So they have to wait 12.6 more minutes.